So I think in problem number 1, everybody was okay. The only thing that I expect to see is that you explain in words actually how you're getting the formula. In words, for example, for A, you say the sum of 3 integers is even if they are all even, or 2 are odd and the other one is even. You explain that before you start writing the formula, or you write probability of 3 even plus probability of 2 odds and 1 even. That it is clear why you're writing this. But if you just start the problem and you start writing this down, nobody knows exactly what you're doing. I didn't penalize for that, but if I see that on the test, I'm going to penalize for that. You need to have clearly written what you're computing. The numbers here don't tell me where you're choosing these things from. And part B, there were 2 ways of answering in B, and almost everybody answered this way. So the probability that the product is even is that at least one of the 3 numbers is even. So if at least one is even, the opposite of that is none of them is even. The opposite of at least one is none. So none of them is even is all 3 are odds. So it's 1 minus the probability of the complement, which is probability that the 3 numbers are odd. Therefore, you get that. And 1.314, you needed to first label the 2 things. I see 2 or 3 people had a problem with this question. And the problem is in not understanding here what it means. Find the probability that they have the same number or same color. This is the same event. It's not 2 different things. It's not find the probability that they have the same color and then find the probability that they have the same number. It's find the probability that they have the same number or same color. So the event is same number or same color. And that event split into 2, that they are same color and the other that they are same number. So it's probability of A union B. That's what is required in the question. And that, by definition in this class, is probability of A plus probability of B minus probability of the intersection. But the intersection is empty because there is no replacement. So the same ball cannot come twice. That's the reason why you can't have 1, 1 with the same color. Therefore, the 2 events are disjoint. That's why the probability of the intersection is 0. So the probability is P of A plus P of B. And now you go around and you compute P of A, P of B, and you add them to get the answer. But to be strict, you need to explain all that, right? Because it's a union, you need to say why you are not subtracting the probability of the intersection. It's because it's 0. It's not for any other reason. Then this problem is the one where I had maybe up to 5 people with issues, and the main issue being forgetting to explain that.
Dr. Longla, you went silent.
What? How is that? Can you hear me?
Yes, sir, we can now. Thank you.
Microphone is still on. I don't know why, but nobody touched it. Can you still hear me now? Nobody answers. Did he hear me or not? Can you still hear me now?
Yes, we can hear you.
We were all nodding.
If you don't hear, I'm not looking at you. Your camera is right there, and I'm teaching here, so I actually don't see your faces. All right, so I was explaining that the issue that most of you have with this question is forgetting to explain right here, what is disjoint? Starting the problem, The probability is the probability of the intersection divided by the probability of C1. To move from here to here, I understand all the steps here. That's correct. Everybody did that correct. C1 intersection with C2, union C1 intersection with C3, and so on. But right there is where the problem is. Forgetting that the disjoint sets are C1 intersection C2, C1 intersection C3, C1 intersection C4, and so on. Those are the sets that are disjoint that you need to mention to transit from here to here. You don't need to find the probability of the intersection of all of them. They need to be mutually disjoint, 2 by 2. That's what you need, not the probability of the whole thing. So this is disjoint with the next one. This is disjoint with the other one. And any two of them are disjoint. And that's all that is important. And on the works of most of you who had that issue, I wrote this, that you should write that C1 intersection with Cj are disjoint. For j not equal to 1. That's the only condition that you need to transit from here to here. You don't need to intersect all these sets to have 0, because that intersection means nothing to this equality here. It changes nothing to it. Am I making sense? And then from there, the rest is easy. That's the only issue that people had there. So now here, this problem, everybody just got 100% on it, so we don't need to talk about that. And right here, in this problem, what I'm missing on most of the work is that you need to give this to me first, this formula. You can't just start writing the numbers. This formula is true. Why? Because they are independent. You're justifying that by independence. Getting this before going there. Okay, and the rest is obvious. Now, something is hidden in this problem that we have actually not done. The last problem I wrote is obvious, but I find at the end when I was reading, one person actually had a problem with it. So what you need to do there is you need to know that it's all about unions. There's no intersection there. Because it's the probability of either 1 or 2, probability of being on an interval. It's the sum of probabilities of everything that falls within that. So nothing else, no product. Okay. All right, now I'm going to write down what I'm saying we didn't do here that you used as a fact, but we never proved it. There is actually a problem in the book that asks you to prove that. So let me do that here. It's an exercise. Show that if A and B are independent, then A and B complement are independent. We never showed this, but you use it in that problem, right? A complement and B are independent. And A complement and actually, okay, I need to point here, right? I want to write and I was putting the sign. You know, if I put the sign and here, I'm wrong, right? Because that would be the intersection, but I need to put the word. And B complement are independent as well. So this is a fact that you all used in that problem, but we never proved this fact. It's another problem in the textbook. Show that if these two events are independent, then these two are independent, these two are independent, and those two are independent as well. Okay. So what can we say? We can say that A is A intersection with B union A intersection with B complement. Do you agree with this? Do you agree that this is true? Yes, right? So if a point is either in A and B or in A and the complement of B. Moreover, A intersection B and A intersection B complement are disjoint. There is no point that is in these two sets at the same time. Therefore, probability of A equals probability of A and B plus probability of A and B complement. By independence of A and B, P of A and B is P of A, P of B. So P of A is equal to P of A, P of B, plus P of A and B complement. It follows that P of A and B complement equals P of A times 1 minus P of B, which is P of A, P of B complement. And that means that A and B complement are independent. So I'm leaving the other two as exercise for you. You can practice on that the same way we did this one. Any question about this and the homework? Anyone with a question? Okay, so we will move on, hoping that I have answered to all the questions that you had after submitting your work. And today, we will be talking about working with random variables.
Dr. Longlow, we can't see that.
I will see if you can see.
Thank you.
Welcome. So we'll be talking about working with random variables. First thing is the expectation of a random variable. Consider separately the case of a continuous and a discrete random variable. And we say the continuous random variable has a PDF, which means probability distribution function, little f of x. And the definition says when integral from -∞ to infinity of absolute value of x times f of x dx is finite, the integral e of x, which is also denoted mu of x, or mu with index x, equal integral from negative infinity to infinity of x, f of x dx is called mean mathematical expectation, or just expectation of the random variable x. So you can see in different books, different names for that. You can see it as mean of x, mathematical expectation of x, or just the expectation of x. And the condition for that to work is first that the integral of the absolute value of x times f of x dx is finite, which means that this is finite as well. So the expectation can never be infinity. The expectation of a random variable is always a finite number. Two for discrete. Random variables. We have a PMF, which is probability mass function, which gives you the probability that the random variable x is equal to little x for every x. Here, F is the density, which actually just tells you how likely we are to fall at a point, but not the probability. Here, this number P of X is between 0 and 1. The density F of X doesn't have to be between 0 and 1. Okay. It's just a positive function with integral equal to 1. Why integral equal to 1? Because the probability of the sample space is 1. So if you integrate over the whole space, you get 1. That's the reason. And that's the only condition that you have on that function, little f of x. That it's positive and the integral is 1. So for discrete, we check the sum. When the sum over all possible values of x, of absolute value of x, P of x is finite. When the random variable takes a finite number of values, this is obvious, because the sum of a finite number of values is always going to be finite. When the random variable takes countably many values, then this turns into a series. And you know that not all series converge. Some converge, some don't. That's why it's important to check that condition when you have countably many values for x. The expected value in this case is taken as the sum over all possible values of x times P of x. for transformations of x of the form y equals g of x, the expected value of g of x, when I ask you to find the expected value of a function of x, you don't have to find the distribution of that function of x before you find the expected value. The expected value is going to be equal to the integral from negative infinity to infinity of g of x. So you don't need to find the distribution of g of x before you find the expected value. You could just integrate g of x, f of x, dx, where f of x is the density of x. For continuous random variables and the expected value of g of x, for discrete random variable is going to be sum over all values of x of g of x, p of x. For discrete random variables. Again, when you want to find the expected value of a function of a random variable, you don't need to find the distribution of that function of the random variable. You just go ahead and plug it into the formula and you get the expected value. And technically, if you actually go find the distribution, then use the original formula to find the expected value, you get the same answer, but you work more in one case. Some properties. Get one, the expected value of k equal k for any constant. For any constant k. So if your random variable is a constant, then the expected value is equal to that constant. It doesn't change. The average of a constant is the constant itself. And then the expected value of ax1 plus bx2 is equal to a expected value of x1 plus b expected value of x2. So the expected value of the linear combination of random variables is the linear combination of the expected values. Some special cases. Before we go to the examples. Special cases of expectation, we call the variance of x, denoted sigma squared, is equal to the expected value of x minus mu squared. That means the expected value of the random variable minus its mean squared. And we easily prove that this is equal to expected value of x squared minus mu squared. So the variance is equal to the expected value of the square minus the square of the expected value. And you have what we call the moment generating function. Which is the expected value of e to the t times x. It's a function of t called the moment generating function because it generates the moments of the random variable x. And what do we call moments of the random variable x? It's the expected values of the powers of x. So if you can find this function, then you can find the expected value of any integer power of x. Like expected value of x, expected value of x squared, expected value of x cubed, x to the 4th, x to the 5th, x to the 6th. You can find them using this function without having to compute any integral if you already know this. E to the power tx. Need to write that here again. The moment generating function evaluated at t is the expected value of e to the power t times x. Example 1. A Bernoulli with parameter p, which means probability that x equal 1 equal p, probability that x equals 0 equal 1 minus p, probability that x equal little x equals 0 elsewhere. Then the moment generating function of this random variable is obtained as expected value of e to the tx. So this is a function of x, right? Because it's a discrete, it's a sum over all possible values of x, e to the tx times the probability that x equal little x. That's what the definition of the expected value is. This random variable being discrete, we need to use the formula of the discrete for it. But how many values of little x there exist in this problem? 2. The only non-zero ones are 2, 0, and 1. So this equals e to the t times 0 times probability that x equals 0 plus e to the t times 1 times probability that x equal 1. That's what that formula means. And the probability that x equal 0 is 1 minus p. E to the 0 is 1, so this is 1 minus p plus probability that x equal 1 is p, so that's p e to the t. So the moment generating function of this random variable is 1 minus p plus p e to the t. Do we agree? Just say yes.
Yes, sir.
Yay, thank you. So now next, after computing the moment generating function, I want to use this example to explain everything else that I was talking about. I said that you can use this function to find the moments of x. And I define the moments of x as being the expected value of powers of x, integer powers of x. So the kth moment of x is expected value of x raised to the power k. That's what I said. And how do we find those things using the moment generating function? Now, this moment generating function, let me say in this example, I want to find expected value of X, for example. I can use the definition to find it, right? But I just want to use the moment generating function to show you how we got that. So I say the moment generating function, if I take the derivative of the moment generating function at 0, then this is the expected value of X. And so I take this function and I take the derivative. So derivative with respect to t of 1 minus p plus p e to the t, then plug in t equals 0. What is it? It's p e to the t, plug in t equals 0. It's equal to p. So the expected value of the Bernoulli random variable is p. Now the question is, why is this true? Right? Why is this true? Notice that by definition, the moment generating function at t, if I take the derivative with respect to t, this is integral. I can switch this with the derivative because we have absolutely integrable functions. You take the integral of the absolute value is finite as well, right? In that case, you can switch the integral and the derivative. And that becomes e to the t x times f of x dx. This is if we are using a continuous random variable. And this, the derivative of e to the tx, what is it? With respect to t. That's integral of x e to the tx f of x dx. Notice that if you plug in t equals 0, what you get is integral of x f of x dx, and that is the expected value of x if you plug in t equals 0. And you prove it the same way for the discrete random variable, just replacing integrals by sums. Does that make sense? And if you want the second one, you take the second derivative. You get x squared down. You take the third derivative, you get x cubed down. Take the fourth derivative, you get x to the fourth down, right? Are we still okay? I see a silence that I don't understand. Expected value of x squared is the second derivative of the moment generating function at 0. When they exist, the expected value of x to the k is the k derivative of that function at 0. That's why it's called the moment generating function. So in this case, expected value of x squared for this example, what is it going to be? Take the derivative of this. It's going to be d over dt of p e to the t. Log in t equals 0, which is p e to the t again. Log in t equals 0, and that is again p. So the expected value of x squared is p. And in fact, for the Bernoulli random variable, the expected value of x to the power k is going to be p for any k. Why is it? Simple to see that. Look here. X to the power k is x. So you all agree with that? For the Bernoulli random variable, x to the power k is x. Why is it? Because x is either 0 or 1. 0 to any power is 0. 1 to any power is 1. So when you raise x to any power, you're not changing anything. It's x. That's why the expected value is going to be the expected value of x, which is p that we found. Okay. Now, that being the case, sigma square for this problem, which is expected value of x square minus expected value of x square, is therefore going to be p minus p squared, which is p times 1 minus p. And this is what you know for those who had it in high school, the Bernoulli random variable. The variance is p times 1 minus p, or p cubed, when you use to denote the probability of failure cube, right? That's why. Any questions? Are we okay with this example? Have important inequalities. Some of the inequalities that we need with random variables in work. When we're done with this, we could check for some more random variables and find the expected values and use that MGF to find other expected values if possible before time ends. So among the important inequalities that we have here, the first of which we think sometimes is the most important is the Markov inequality. In any course, you will see this guy. Let's say let u of x be a non-negative function if expected value of u of x exists, then probability that u of x is larger than or equal to c is less than or equal to expected value of u of x over c. Very strange, right? So if we have a non-negative function and we know the expected value of that non-negative function exists, which means it is finite, then we can always find an upper bound for any c on the probability that u of x is larger than c as the expected value divided by that constant. Why is this the case? Now let me here assume the case that it is continuous. Even if it's if it's discrete, you're going to prove it the same way. Okay, just using sums instead of integrals. Okay. So here, if I'm assuming x is continuous, adding absolutely right, then expected value of u of x is equal to the integral from negative infinity to infinity of u of x little f of x dx. That's the definition. And that integral splits into two. That's the integral of u of x f of x dx over two different sets where u of x is larger than c and where u of x is strictly less than c. Do you agree with that? The entire space splits into two. Either u of x is less than 1, less than c, or u of x is larger than c, right? No matter where x is. It's either here or there. Do we agree on this? All right. And this thing, given that the function u of x is positive, u of x is positive, that implies that u of x, f of x is positive because f of x is positive as well. Therefore, this component here is positive. This integral here is positive. And that implies that the expected value of u of x is larger than or equal to the integral over u of x, larger than c of u of x f of x dx. Are we in agreement? Because u of x is equal to this plus something positive, then it's larger than that. Now, because in this integral, u of x is always larger than c, then this thing is larger than or equal to the integral of f of x dx over the set where u of x is larger than or equal to c. Times c. Replace u of x by c, you get something that is smaller because u of x is larger than c. That being the case, get the expected value of u of x larger than or equal to c, and this integral over the set where u of x is larger than c is nothing but the probability that u of x is larger than c. Remember that p of a is integral over a of f of x dx, right? Remember that? So this is by definition. P of A is integral over A of f of x dx. That's the definition that is used here to get from here to there. And therefore, you can solve and have probability that u of x, this is capital X, okay, is larger than or equal to C, is less than or equal to expected value of u of x over C. And C here is a positive number, of course. So that's it. That's the end of the proof of the Markov inequality. So we have Chebyshev's inequality. If x is a random variable with mean, mu, and variance sigma squared, then for any k strictly positive, probability that absolute value of x minus mu is larger than or equal to k sigma squared is less than or equal to 1 over k squared. This is used in statistics a lot to approximate probabilities. So mu is the mean, sigma square is the variance. So which means this technically would mean that the probability to be k sigma squared, the probability to be k sigma squared away from the mean is less than 1 over k squared. The probability to be 2 standard deviations away. Sorry, this is k sigma, okay, sigma squared. Sigma squared is the variance, but that's a standard deviation. We need to square it before we get to the variance. The probability to be k standard deviations away from the mean is less than 1 over k squared. If I want to be 3 standard deviations away from the mean, I know the chance of that happening is less than 1/9. 2 standard deviations away, the probability is less than 1/4. Okay. So the proof of this is based on the previous one, on Markov's inequality. You can just turn this thing and say it's equal, because these two numbers are positive, you square them. It's equal to the probability that x minus mu squared is larger than or equal to k squared sigma squared. And look, this is a positive function of the random variable x because the square is never negative, right? So the condition of the Markov's inequality is satisfied, and therefore this thing is less than or equal, here you say Markov. So by Markov's inequality, this probability is less than or equal to expected value of x minus mu squared over k squared sigma squared. But the expected value of x minus mu squared is sigma squared. That's the definition of sigma squared over k squared sigma squared, and you get that it's less than 1 over k squared. So next time we move to chapter 2. This will be the end of chapter 1. One last inequality before, if we have time to solve one problem. What is it, time already to go? I think we still have enough time, right? 20 minutes?
I have a question.
Yes,
What you are saying?
yes.
We have
The Markov's inequality claims that the probability that u of x is larger than c is less than expected value of u over c for any positive function of x. Now, here, probability that x minus mu squared larger than or equal to k squared sigma squared. C is k squared sigma squared. And that's a positive function of the random variable, x minus mu squared. It's never negative. What's that? Well, that's exactly the Markov property, which tells me from there that this probability is less than the expected value of this random variable that is here, divided by the constant that is here. And that's what the ending here is in that theorem. It's less than expected value of the random variable that is here, divided by the constant that is here. And so here, I have x minus mu squared, which is a positive random variable, positive function of x. And I have k squared sigma squared as the constant c in the theorem. So it goes where c is, then on top you have the expected value of that function, which is x minus mu squared. Now you use the definition of the expected value to know that the expected value of x minus mu squared is sigma squared. That's the definition of the variance. And that was at the beginning of the lecture. So you just replace that by definition by sigma squared, and then the sigma squares just cancel, and you get 1 over k squared. Yes?
But this is also positive x minus mu mod. This is also positive, so why can't we use Markov inequality in the very first?
On x minus mu absolute value? Because if I ask you what's the expected value of absolute value of x minus mu, you don't know. That's the problem. So it's not a known quantity. You can compute it. But in most of the problems, for most of the distributions, sigma squared is known. And it's easy to compute. Okay? But to compute the expected value of absolute value of x minus mu, anything else? And again, this is just establishing these results that already existed, right? So if you change to get to something else, that might still be true, but not useful for the case at hand. Anybody else with a question? I would love to have a question from the cameras that I'm seeing here. Are you guys still with me? Everything okay? Okay.
Yes, sir.
Yes.
I see, Melissa, I saw that. All right, now everybody is happy, and except for one or two guys here that are not happy, I don't know why. Is everything okay? Yeah. I know you're fine, so. Yeah. Unfortunately, with mask now, people don't see me smiling. I'm trying to smile and get people to smile, but the mask is covering my smile. I have a nice smile, you know. So, no, rarely it comes, but anyways, let's do the last one. And again, sorry that the first part of this course is more about explaining this theorem, because what I expect the most is for you to be able to prove these things that needs to be used in the next chapters of the class, okay? It's not much about solving questions with numbers, but understanding the theory here at this point and how to use it to answer questions. All right, D3. And that will be Jensen. And the last guy, inequality. No more after that. If I put another one after this, you say no, you said it was the last one. So, Jensen's inequality claims the following. If phi is convex on I, which is an interval, and X is a random variable, with support contained in I and has finite expectation. Then this is a very funny guy. Phi of expected value of X less than or equal to expected value of phi of X. So you don't need to worry yourself taking expected value of phi of X. You know that it's always going to be larger than phi of expected value of X. And I will invite you to read theorem 1.10.4 if you have time. 1.10.4. And that theorem 1.10.4 gives you the different instances when you can conclude that a function is convex. Okay. That's what this part is about. So please take time to read that. Now we're gonna do some examples. let's see, we have X has distribution. F of X equals X plus 1 over 2 when minus 1 is less than X less than 1 and 0 elsewhere. And then I would say 1 find MGF of X, find the moment generating function of X. Mx of t is expected value of e to the t times x, which is, in this case, integral from -1 to 1. Should be from -infinity to infinity, but we know that the density is not 0 only between -1 and 1. So everywhere else it is 0. So we just integrate from -1 to 1. And you need to have e to the tx times the density, and the density is x plus 1 over 2 dx. So we need to compute this integral. We do it by parts. This is going to be x plus 1 over 2 times e to the tx over t, plug in x equal -1, then 1, minus integral from -1 to 1. The derivative of this is 1/2 times e to the tx over t dx. When you plug in 1 here, you get 1 plus 1. That is 2 over 2, 1. So you get e to the t over t. When you plug in -1 for x, you get 0. And minus 1 over 2t squared e to the tx. Then you plug in -1 and 1 for x. This gives you e to the t over t. Then you plug in x equal 1, you get e to the t over 2t squared. Minus, when you plug in -1, e to minus t over t squared. So that minus minus becomes plus. So that's what the moment generating function would be. find the expected value of X at sigma square. By definition, the expected value of X is integral from -1 to 1 of X times the density, which is X plus 1 over 2 dx. So that's integral from -1 to 1 of X squared over 2 plus X over 2 dx. So that's X cubed over 6 plus X squared over 4. Plug in -1, then 1. This is going to give us, when I plug in 1, I get 1. When I plug in -1, I get -1. 1 minus -1, that's plus 1. So that's 2 over 6, 1/3. Plus, I plug in 1. 1 squared is 1. -1 squared is 1. 1 minus 1, 0. So the answer is expected value of X equal 1/3. And to get variance of X, you need to find expected value of X squared first. That's integral from -1 to 1 of X squared times X plus 1 over 2 dx. This is integral from -1 to 1, X cubed over 2 plus X squared over 2 dx. You integrate, you get X to the 4th over 8 plus X cubed over 6, plug in -1 and 1. When you do so, when you plug in 1, you get 1 minus 1, you get 1, so that's 0 plus. You plug in 1, you get 1/6, minus 1/6, so that is 2/6 again. Is that okay? Everybody agrees with me?
Will you move your paper over just a little bit?
Does everybody agree that this calculation gives 1/3 as well? Please check with me. I'm not good at algebra. You agree it's 1/3 for X squared?
Yes.
All right. Thank you. Now we got expected value of X squared. We got expected value of X. Now we can find sigma squared. Let me just put that at the end here, not to start a new paper at the end of the lecture, right? So sigma squared equals expected value of X squared. This is the alternative formula minus expected value of X squared. So that is expected value of X squared 1/3 minus expected value of X 1/3 squared. Okay. So there are two ways of computing the sigma squared. Either take the expected value of X squared and subtract the square of the expected value, or start from scratch and find the expected value of X minus mu squared. Nobody wants to do that right now. I don't want to do that. If I know expected value of X squared and I know expected value of X, I just do this and I get the answer. So that's 1/3 minus 1/9. That's 3 minus 1, 2, 9. So this is the variance. I wanted to go all the way to write down what the theorems will look like, but it seems I'm running out of time. Would you guys give me 5 minutes to finish that part? To write down the Jensen's inequality, Chebyshev's inequality, and Jensen's inequality for this example, what it would look like. Okay. So here, Jensen's inequality. Yeah, I'm starting by the last one, but let's start by Markov first, just in the order we had. Markov inequality would mean, because here x squared is a positive function, thus probability that x squared is larger than or equal to k is less than or equal to the expected value of x squared over k. That's what that means. And we got the expected value of x squared in this problem to be 1/3. So that's 1/3 over k. So 1/3k. So in a problem, for example, in statistics, if you run forward, you can say, find a lower bound. Sorry, find a no lower, but find an upper bound. Find an upper bound on probability that x squared is larger than 9 for a given random variable. In this case, we get -1 and 1, so we can put here, say, larger than 1/2. Okay, just to be consistent with the example that we have, because for this example, x is between -1 and 1. Okay. So the probability that x squared is larger than 1/2 for this problem, and the answer would be probability that x squared is larger than or equal to 1/2 is less than or equal to 1/3 times 1/2, which is 2/3. So the probability that x squared is larger than 1/2 does not exceed 2/3. And Chebyshev's inequality would be probability that absolute value of x minus the mean is 1/3 larger than or equal to k. Sigma here is square root of 1/3. Sorry, sigma is square root of 2/9. Okay, because sigma squared is 2/9. We found sigma squared in this problem to be 2/9. So this probability is less than or equal to 1/k squared sigma squared, k squared times 2/9, which is 9/2k squared. That's what the theorem says technically. And Jensen's inequality would say, in this case, what's that? Expected value of x squared is larger than or equal to expected value of x squared. And the function here, phi of x in this case, is equal to x squared. And in that theorem that I wanted you to read, if you read that theorem, you'll figure it says that when the second derivative is positive, then the function is convex. So you take the derivative, the second derivative of this function is 2. 2 is positive, so it's a convex function. And therefore, I know without even computing them that the expected value of x squared is larger than the expected value of x squared, right? That's what the theorem says. What is it in fact? We have computed this. We have computed the expected value of x squared. It was 1/3. We have computed the expected value of x. It was 1/3 squared. Is this true? Yes, the theorem is not lying, right? So this is technically what the theorem is saying. That's what we found. It's the same thing. All right. Thank you very much. Then. Any other questions? Nope. All right.
Do we have class on Monday, on Labor Day?
Oh, no, no. Unfortunately, I would love to be here, but they said no. So
Okay, thank you.
you're welcome. See you next time.
See you next Wednesday.
Our next meeting is on Wednesday, right? Wow, that's so long. 1 week. All right. Bye. See you next week.